1 or 2 more minutes? Yeah? 1 minute, yeah? Good afternoon, everybody. Welcome back to the sessions. We now start the session observing Arctic ice ocean atmosphere interactions, changes and effects on interannual to centennial timescales. And I just read up the session committee because that's not listed here. That's Laura de Steur, Aro Olsen, Katrine Husum, Agnieszka Beczynska-Möller, Signe Orboe, Agneta Fransson, Pauline Snöyes Leon Malm, and Gunnar Spreen. And this session deals with the spheres, the atmosphere, the sea ice, and the ocean, and the linkages, the interactions, the effects of climate change, and a main focus is on observations of this. So we are very excited that we got so many interesting contributions submitted. So this theme is split into 3 sub-sessions, and today we have the first one of that. The second and third are tomorrow morning and before lunch. So please also check out those. There's also a poster session later today at 17:30 in the Fram Center, not long to walk from here. So there will be poster presentations about the same topic. And coming back to today's presentations, they are mainly about sea ice, but also visiting related subjects. And we have first a keynote, and then we have a number of other talks. And the keynote is by Hiroshi Sumata and others from the Norwegian Polar Institute, and it's about the sea ice thickness in Fram Strait. So I'd like to invite Hiroshi Sumata to the stage. The floor is yours.
Yeah, thank you, Sebastian, for introduction. My name is Hiroshi Sumata from Norwegian Polar Institute. Today, I talk about regime shift in Arctic Ocean sea ice thickness captured by Fram Strait Arctic Outflow Observatory. Okay, let's start from the short introduction. This is a sketch of the mean sea ice motion in the Arctic Ocean. The small navy arrows show the mean sea ice motion derived from remote sensing. And the green lines are track of ice-tethered buoys that arrived in Fram Strait. Fram Strait is shown by yellow line here. And the yellow big arrow is a transpolar drift stream that carries sea ice from the central Arctic to Fram Strait. So as you see, the large fraction of sea ice in the central Arctic come to Fram Strait sooner or later. So actually, about 90% of, sorry. Okay, thank you. So as you see, the large fraction of sea ice in the central Arctic come to Fram Strait. So Fram Strait is an ideal location to monitor the long-term changes of sea ice in the Arctic Ocean. And then Fram Strait Arctic Outflow Observatory has continuously monitored the thickness of the outflowing sea ice for the last 3 decades. So the Fram Strait, this is a sketch of the Fram Strait section, and red box is the Fram Strait Arctic Outflow Observatory here. And here we have ocean moorings. and which measures the ice thickness together with ocean properties. This is a sketch of moored instruments, and on top of each mooring, we have upward-looking sonars, which continuously measure the underwater fraction of drifting sea ice. And then retrieved data are processed, calibrated, and validated for analysis. I show you the data obtained from this observatory. Okay, first, this is a sea ice thickness distribution observed in Fram Strait. This figure, the horizontal axis is the ice thickness, and the vertical is the ice thickness frequency measured by upward-looking sonars. The blue line is the thickness distribution. This is the average from 1990 to 2006. And the shade is the standard deviation. From this distribution, we can identify different types of sea ice. The fraction of ice thinner than 1 meter here is new young ice formed in the vicinity of Fram Strait. And also, in this distribution, we see a modal peak around 2.7 meter. This is a fraction of level sea ice, mainly formed by thermodynamic process. And also, we see a long tail toward very thick ice, 4, 5, 6, 7 meters. This is a dynamically grown sea ice by ridging process. And this figure compares the thickness distribution before and after 2007. Blue is again the thickness distribution before 2007, and orange is after 2007. So we can clearly see a significant difference. One is a reduction of modal ice thickness. About 1 meter decrease occurred between the two periods. And also we see the increase of the fraction of ice in the mode, nearly 70%. And also we see the decrease of thick deformed ice, about 50%. And this is a time series of sea ice thickness distribution from 1990 to 2019. The vertical axis is ice thickness, and in this figure, the intensity of the color shows the amount of ice observed in each ice thickness bin. So again, we can identify different types of sea ice, new young ice, level sea ice, and ridged ice. And if we focus on, we can see the zonal band here, ranging about 2 to 3 meters. This is a fraction of level sea ice. And if we focus on the intensity of the color of the zonal band, we can clearly see the sudden increase of the intensity of the color around 2007. So something happened at that time. In order to examine the change of the ice thickness distribution, we examined the modal peak height and the variance of each distributions. Now the middle panel shows the time series of modal peak height, and the bottom is the variance of thickness distribution. So again, we see a sudden change of these thickness distribution properties. So after 2007, the modal peak height was suddenly increased, and the variance was suddenly decreased. From these changes, we can identify two sea ice regimes. Before 2007, ice was in thick and deformed ice regime. And after 2007, ice is in thin and more uniform ice regime. Such a change can be also seen in the fraction of very thick ice. Now the top panel shows the fraction of ice thicker than 4 meter and 5 meter. Again, we see a sudden reduction of the fraction of the very thick ice. And if we apply sequential t-test for regime shift detection, we can clearly identify two regimes. So now we ask a question: why sea ice thickness distribution in Fram Strait has suddenly changed in 2007. To answer this question, we examined the pathways and the residence time of sea ice in the Arctic Ocean that arrived in Fram Strait. These two panels show sea ice trajectories and origins of ice flows that come to Fram Strait before and after regime shift. The left panel is the situation before 2007, and right panel is after 2007. In these panels, the gray clouds show the pathways of sea ice, and the dots, color dots, shows the allocation of initial sea ice formation. And the color of the dots shows the time of sea ice formation relative to their arrival in Fram Strait. If we see the pathways of sea ice, we don't see any significant difference. But if we focus on the color of the dots, we can clearly see the difference. So before 2007, ice was formed about 4 years before coming to Fram Strait. But after 2007, ice was formed 2 to 3 years before coming to Fram Strait. So significant drop of residence time of sea ice occurred at that time. Now the bottom panel shows the mean residence time of sea ice in the Arctic Ocean that arrived in Fram Strait. So we see two-step drop of residence time occurred in 2005 and 2007. So by this shift, the mean residence time was reduced from more than 4 years to less than 3 years. So about 1.6 years reduction occurred. The reduction of the residence time was caused by drop of summer ice extent in Alaskan and Siberian sectors. This figure shows the difference of September sea ice concentration before and after 2007. So we see large drop of September sea ice concentration in sea ice formation areas. And this is a time series of these two areas. And dashed lines are regimes detected by sequential t-test. So we see the drop occurred in 2005 in Siberian sector and 2007 in Alaskan sector. So after the shift, sea ice in these areas cannot survive summer melt. And every year, new ice was formed in this area. This is one reason the residence time of sea ice has suddenly decreased. And also, the faster sea ice motion after 2007 contributed to the shorter residence time. Left panel shows the difference of ice drift speed before and after 2007. So we can see the intensification of Beaufort gyre and also acceleration of transpolar drift stream. And right panel is a time series in these three areas. So annual mean sea ice drift speed. So all three areas, again, the dashed lines are regimes detected by sequential t-test. So in all three areas, the mean drift speed was increased after 2007. So in summary, the two-step drop of residence time, which was about 1.6 years, was caused by summer sea ice retreat in ice formation areas, that is Alaskan and Siberian sectors, and also acceleration of drift speed after 2007. The thickness distributions we observed, the change of the ice thickness distributions we observed in Fram Strait is explained by shorter residence time. So again, the left panel is the ice thickness distribution we observed in Fram Strait, and now the right panel shows the results from a stochastic ice thickening model that describes dynamical ice thickening process together with thermodynamic ice growth. This figure describes how the ice thickness distribution evolves in time. So initial ice thickness distribution is a normal distribution with a solid line, and after 1.5 years, 3 years, 4.5 years, it describes how the thickness distribution changes. So for longer residence time, the distribution has smaller modal peak height and heavy tails toward very thick ice. So the change of the thickness distribution in Flamstrait can be explained by a simple theoretical framework as a consequence of the shorter residence time. Okay, until here is a solid outcome of the study, and the following is a discussion. So what is the possible consequences of the regime shift? This is an ongoing and also future topic, I would say. And one is sea ice condition is expected to be more sensitive to anomalous atmospheric events. So these are the sketch of the sea ice situation before and after the regime shift. So before the regime shift, sea ice floes has deep keels penetrating into the ocean, and this prevents sea ice to move when wind forcing applied at the surface. But after the regime shift, ice has shallower keels, so ice can be easily moved by wind. And also, thinner ice easily melts away by atmospheric or oceanic heat supply. One possible example is the unprecedented decline of Arctic sea ice outflow we observed in 2018 in Flamstrait. This is a time series of southward volume flux in Flamstrait at the Flamstrait section, and in 2018 we observed the record minimum, which was less than 40% of the average of the previous decade. And this was caused by anomalous sea level pressure pattern. The left panel shows the sea level pressure anomaly and 10-meter wind in February 2018. We see the dipole pressure anomaly in the Atlantic sector of the Arctic and the associated southerly wind. And then this pressure pattern caused the record minimum. But if we see the time series, this is a light panel is the time series of meridional wind, and the orange shows the southerly wind event. So other than 2018, such an anomalous event sometimes happened, but only recent years, 2013, 14, and 2018, we saw a minimum export of the sea ice in Flamstrait. So thinner and mobile sea ice condition after the regime shift could have made sea ice more sensitive to anomalous atmospheric events. Okay, this is a summary of findings. Flamstrait Arctic Outflow Observatory captured regime shift in Arctic Ocean sea ice thickness in 2007. The shift was from thicker and deformed ice regime to thinner and more uniform ice regime. The shift was caused by a drop of the mean residence time of sea ice. And the reduction of the residence time was caused by a drop of summer ice extent in Alaskan and Siberian sectors, occurred in 2005 and 2007, and also by acceleration of ice drift speed after 2007. Next. Yeah, this is acknowledgements. This study was supported by two external funding. One is a Fresh Shark project supported by Norwegian Research Council, and the other is Crisis, supported by EU Horizon 2020. Thank you for your attention.
Thank you very much, Hiroshi, for this very interesting talk. We have time for a question. Please. Here comes one with the microphone.
I'm Shotaro Uto from Hokkaido University, Japan. Thank you very much for very interesting presentation. I have one question, question. So you find out so the residence time and faster motion may enhance the thickness change. But I guess so. So if if sea ice moves faster, so some ridging may enhance ridging, and to some degree balance between residence time decrease and ridging process, intensity of ridging process. Is that right? Or is it negligible?
Yeah, I think that is one of the ongoing and also future topic, because the actual ridging process, we can't capture actual ridging process. Only before ridging, after ridging, we have some thickness distribution, but real-time monitoring the ridging process is quite difficult. And one possibility could be the ridged ice was formed close to the coast, the ice formation areas. Because if you have a coastline, and then the tide and the inertial motion push the ice, and also wind forcing sometimes push the ice towards the coast, and then ridging occurs. And the Central Arctic, it's a bit different from the Central Arctic. And the ridging process across to the coast was disappeared after 2007. That could be one of the cause, I think. But it's a future study topic. Thank you.
Well, thank you again, Hiroshi Sumata, for this great talk, and that was an excellent introduction and background about the Arctic sea ice and the interactions with ocean, with atmosphere, and how the linkages and consequences of the changes are. So I also want to encourage to use the time in the break after the session to discuss more with the presenters here, since our time for questions here is limited. But I'd like to move over to the next speaker. That is Edmund Hansen from Norse here in Tromsø, and he will speak about coupled sea ice thickness and ocean heat variability in the Barents Sea. Edmund, the floor is yours.
Yes, and these technicalities, do I manage?
You will. Microphone, and here's to switch further, and here's your time shown.
Okay, am I online, on there? Yeah, thank you for that introduction, Sebastian. As you all heard, my name is Edmund Hansen. I come from Norse, and I'm up here on the podium to talk about coupled sea ice thickness and ocean heat variability in the Barents Sea based on some recent observations. So, sea ice draft has been observed in the Barents Sea by 5 upward-looking sonars. You saw an illustration of that in the previous talk. Since 2014 by Equinor and partners. I show the location of the instrumentation over here on this map. 2 instruments on Spitsbergenbanken, 3 instruments on Storbanken. I also show, hardly visible because it's in yellow, the maximum sea ice extent of the winter of 2016. That's this yellow line. So that was a year, 2016, with particularly little, exceptionally little sea ice in the Barents Sea. Similarly, I show in black here, that's the maximum sea ice extent of the winter of 2020, which was a more normal year in the Barents Sea in terms of sea ice extent. So please remember this difference in sea ice extent. That's quite a central point of my talk as I wrap it up. Well, all the details of these observations you will find in this paper that you see on the screen here over to the right, Cold Region Science and Technology. That is very technical. I'm not going into these technicalities here. I would rather like to take the opportunity in this setting, I mean with this meeting and this topic, to put these observations or parts of this observation into the context of the recent warming of Svalbard. Because that warming is driven mainly by sea ice decline. So increasing sea surface temperatures is one of the factors also contributing, but it's mainly due to sea ice decline. I'll get back to this figure with the increasing temperatures later. So these are my results. With this slide, I want to show you that the draft of locally formed level sea ice increased by approximately 8% per year over this 7-year-long observation period. I have underscored that I'm talking about level sea ice and locally formed level sea ice. And this is important because with level ice, the draft is controlled by thermodynamics only. So there's no ridging, no deformation, there's only, melt and freeze. That it is locally formed means that it is controlled by local processes, or local thermodynamics, as opposed to sea ice imported from the Arctic Ocean, which would be controlled by, where the thickness would be controlled by processes far upstream of our observation site. So this figure, what you see there, that is this almost blur of colors. That's a time series of monthly mean draft of level ice per calendar month. So you can observe, oh, I shouldn't fall down here, these green squares, that's the values for March. And you should also be able to see this black stippled line. That's a linear regression trend, bluntly taken through the months of March, to quantify then this increasing trend that I have provided up here, the 8% increase per year. So you see, the long-term average that is close to 0.6 in this region. You see this increase from approximately 0.4 until 0.7 at the end. And you should also notice, I didn't get this laser to work properly. The great sea ice thickness of April 2020 and May 2020. Now that is the thickness of ice imported from the Arctic Ocean. I'll get back to that on the next slide, but this is also the reason why I have taken this regression line through the months of March. I'm only after the local ice because I'm interested in the local processes. So, what happened? Why did we have this increasing thickness in sea ice in the Barents Sea in a time where sea ice elsewhere is just diminishing in extent? It happened because we had a gradually colder ocean locally. And that is what I show on this figure here over on the left. That's a time series of sea temperature at observation sites. Spitsbergenbanken, upper panel, Storbanken in the lower panel. So I would like to point your attention to two main features of this data set. First, you should notice this, that the summer sea temperatures are decreasing significantly over this period. Secondly, you should notice that the duration of temperatures at freezing during winter has more than doubled from 2016 and until 2020. And the effect of both these features of this dataset, that is to increase the thickness of the ice. When you have lower summer temperatures, you start the freeze up earlier, and you are able to freeze a thicker ice cover over the coming winter season. When you have an extended duration of temperatures at freezing during winter, that basically means that the oceanic part of the melting at spring is delayed. So you are able to maintain this greater thickness for longer then. And here is my interpretation of what's going on then when it comes to the temperatures. This cooling, that decrease, that is an external signal. That's an advective signal associated with variability in temperature and volume transport of the Atlantic water flowing into this region. The extended duration of temperatures at freezing during winter, that is a local effect following from this externally forced cooling. And what happens there is that you have a thicker ice cover, and the atmospheric part of the melting, so the increasing air temperatures, the increasing solar radiation as you progress through spring, needs longer time or is delayed with respect to opening up the ice and exposing then the ocean surface to the solar heat. So you delay the uptake of solar heat. So that little effect, it's actually quite a neat little effect, or at least what is neat is that we're able to quantify it. that's actually then a positive feedback mechanism, amplifying the effect of the externally forced cooling. And that effect is even further amplified by this anomalous inflow of Arctic sea ice that we saw in the previous slide happened in 2020. And I refer to a couple of papers down here that is, they are discussing this inflow, where you simply then you provide more thick ice and you amplify this effect of the delayed oceanic melting. So here's my final slide. I will wrap up everything here. This will be like a conclusion. So what I've just shown you, that is in effect an ocean, sea ice, atmosphere loop, interaction loop, that operates in the direction of lowering the air temperatures at Svalbard. So we have a colder ocean, some influence directly on the air temperatures in Svalbard that you see down on the right. But the biggest effect that goes through this loop, or half loop, you have a thicker local sea ice, you have a lower spring sea surface temperature, you have an inflow of thick Arctic sea ice that happens at the same time, amplifying this effect, and you get a greater sea ice extent. And that is what I'm showing. Over here, you see the, or maybe you're not able to see it, but anyway, the figure shows the long-term decreasing trend of sea ice extent since 1980 in the Barents Sea, on which there is superimposed a short-term increase since 2016 and beyond 2020, which then leads to a short-term decrease in the air temperatures at Svalbard, superimposed on the long-term increase. Okay, there was a lot of directions there, increase and decrease, but you see the figures, maybe that helped. So my last comment here would be that I don't claim that this is, that I have discovered something new here. This is a well-known loop. What is new here is that we are able with or observations like this, the one that Equinor has been carrying out, is to quantify the relation between the sea ice thickness, the variability in ocean heat, and how this sea ice thickness interacts then with, or shows up in the sea ice extent. So that's the new part. So I think I end it here, and thank you for listening.
Thank you very much, Edmund, for this interesting talk. One quick question. I don't see, well, there's one there. Philip?
Thanks, Edmund. Very nice talk. I was wondering how fast does it return back to the pre-cold conditions if you have a year or two of warmer ocean and atmosphere conditions? Does it swing back very fast?
I think that happens, on what is that called, intra-seasonally. So it follows immediately with the sea ice extent.
Well, thanks again, Edmund. We move over to the next speaker, who is Robert Ricker, Unlocking Arctic Sea Ice Dynamics, Daily Drift Aware Satellite-Derived Sea Ice Thickness Maps. Robert is also from Norse in Tromsø. Robert, the floor is yours.
Yeah, thank you very much for the introduction, Sebastian. I'm also from Norse, Robert Ricker. I'm in the Earth Observation Group at Norse. And I would like to talk about unlocking Arctic sea ice dynamics from daily drift aware satellite-derived sea ice thickness. So we've just seen that sea ice thickness plays a very important part for the Arctic climate system, and that we can measure it very accurately with ULS, for example, outlooking sonars. But now I want to go up into space basically and talk a little bit how we can observe it better from space. So this is a work that has been conducted with some colleagues, especially from the Met Norway, but also from the Alfred Wegener Institute, and it's in the framework of a project with the European Space Agency. Okay, I want to start with this photograph, with this picture. So it basically shows the sky with stars, and the photo is done with long exposure time. So what you see is this motion blur. And now, what does that have to do with freeboard and thickness maps? So we measure sea ice thickness in the Arctic mostly with altimetry. And altimetry, unlike optical sensors, where you get nice images, where you just need like a day to basically cover the entire Arctic sea ice. With satellite altimetry, you only get measurements along a very thin, along the narrow satellite track. So that means you need to, so this is an example of a daily trajectories over the Arctic from a satellite altimeter. In this case, it's ISAT-2. Yeah, that happens. And so that means we need to collect and aggregate those measurements over 1 month to get a sufficient coverage over the Arctic. And then what is basically done is we just grid. We just average on a Eulerian grid, basically. So this is a 25-kilometer grid, and this is the maps you may know where that are out there and that you can also use. So these are the monthly maps. But of course, what we know is happening is that the sea ice is drifting. As with the stars, where we need a long exposure time to catch them, we also have a long exposure time basically to map the Arctic sea ice thickness. And what we also get then is some kind of motion blur because the sea ice is moving. So again, here you see like this is daily trajectories from ISAT-2 again across the Arctic. And when you just look what happens within 1 month, you see that the ice is actually drifting quite significantly over 1 month. So it's up to 200 kilometers or even above. And of course, if we then like just average, plain averaging, we kind of get a location error, like motion blur into our monthly maps. So how can we solve this? So this is the concept of this drift awareness we are applying. So we basically, so at every cell here, every little box is a daily collection of satellite tracks, of trajectories. And then we track them basically. So we divide each trajectory into parcels, and each ice parcel is like 10 kilometers wide. It's like a round circle. And these parcels we track with the help of ice motion products provided by Met Norway. And this we do like on a daily basis, and then we basically stack those trajectories until we have a full stack that we define here for 15 days. And we do this in both directions, so forwards and backwards. That means we get a stack of 30 days, which is then again like 1 month, so we have like a sufficient coverage over the Arctic sea ice. And so for each step, we drift correct the altimetry measurements so that every parcel at a certain time step is drift corrected. And what we also do is we kind of, because we are tracking and we are advecting the parcels, we can also find out when those trajectories are actually have a crossover at certain steps of time. So you see here, like this is like in the vertical, that's the time axis basically, and we get basically like snapshots of those trajectory at each time step. And because we do the drift correction, we know that the parcels represent the sea ice at a certain time when the satellite was flying over. So if they collocate within a certain area, so here it's like a 25-kilometer box, we find those areas where we have measurements of the same sea ice, but at different times. So that means we can actually determine the growth within those areas because the satellite flew over several times over the same sea ice. And so these areas, of course, it's only possible when you have those crossovers, or if the sea ice is drifting so that the satellite is passing by again. And so you can come up with just a linear, so that's what we do here, just a linear interpolation. Oops, one back. Just a linear interpolation over those measurements of sea ice thickness within these 30 days. And then we get an estimate of the ice growth within this 30 days. And then we can interpolate it on the map. So this is already smoothed. So of course we don't have estimates for each point, but then we can do some interpolation, and then we get those maps of ice growth within these 30 days. And this ice growth we can then use to correct for the ice growth within these 30 days, because if we project all the motion onto one day, of course ice that has drifted over 15 days is growing because of thermodynamic growth, because of dynamic growth. And for this ice growth, we are correcting here using these estimates. What we do in addition is we apply a model because we want to know if our ice growth estimates are actually correct. So this is just an example of one ice parcel we are considering here, and this is just drifting here around the North Pole. And then we use the sea ice thickness distribution from this ice parcel in the beginning, when the satellite measured the sea ice. And we also have the ice parcel at the end, when the satellite was flying over the same sea ice again after 30 days. And then we initialize our initial sea ice thickness distribution. We use it to initialize a column model that we basically apply to the ice parcel, and then we get the modeled ice thickness at the end of the trajectory. And we see here it matches up quite well. I mean, just looking at the mean sea ice thickness and also the distribution. So that gives us some confidence for our estimates, but also for the model. Now, how does it look like if we apply this for all the trajectories we collect and then just grid it on a Eulerian grid? So these are examples here from Envisat from 2002, and then Cryosat, winter 1920. And we see very nice here how we get these daily maps, and we kind of catch the dynamics. We see how the sea ice is flowing. And we also see there's, here with Envisat, we still see the thicker ice here, which then has at some point disappeared in the 2010s. And this really helps us also to understand how dynamics, for example, here in the Fram Strait, it also helps to calculate sea ice export and in general sea ice volume fluxes, because you get much better estimates of the sea ice thickness. And then again, so this is the same period here for Cryosat 2. And here what we also calculate is the convergence, because we apply drift estimates for the correction. So we can also actually calculate the convergence and also shear. And what you see here, for example, you have indicated convergence in the Baffin Bay here on the western side. And you also see that this correlates quite well here with the gradient across the Baffin Bay. So you have the thicker ice here in the west because it's like pushed towards the coast, and therefore it thickens. And this is what you see here. So it's the red area, which is indicating the convergence. And that's basically it. That's what I wanted to show you, and I leave you just here with a taking home message. Yeah, I would like to thank again the collaboration partners, and this is part of the ESA project climate change initiative, which is dedicated to develop long-time series of essential climate variables. And this is ongoing work, so we'll keep you updated, and thank you very much.
Thanks very much, Robert, for this very interesting talk. There's a very quick question. No, that's not the case. Then please meet Robert in the break for more discussions. Thanks again. And I'd like to introduce the next speaker, Wei-Ching Chu from Tsinghua University in Beijing. The microphone. And she will speak about satellite remote sensing of marginal ice zone in the Atlantic Arctic by delay Doppler radar altimetry of Cryosat-2. It's working?
Yeah.
Yeah, okay. The floor is yours.
Yes, thank you for your introduction. I'm Wei Xing from Tsinghua University. It's my honor to have the opportunity to introduce my recent research about the retrieval of marginalized zone with Cryosat-2. And I will start from background. Based on the definition of WMO, marginalized zone is defined as the ice-covered region which was affected by waves. And there are some complex and important interactions between the atmosphere, ocean, and the sea ice in this region. And it's also the key region for the sea ice change with the climate change. And in this research, we will mainly focus on Atlantic Arctic. There is also the key region for the Arctic sea ice change in cold season. And actually, due to the difficulty to retrieve marginalized zone, as well as the lack of observations, we always use the sea ice concentration to define marginalized zone, where the sea ice concentration was between 50% to 80%. But however, with this definition, we can't explain the physical processings in marginalized zone. Thus, it's very important to try to retrieve marginalized zone with satellites. And there shows some methods to observe marginalized zone with satellites, like the high-resolution star image Sentinel-1 and optical image Sentinel-2. We can observe some wave-like feature and identify the flow size distribution with these high-resolution panels. And we can also retrieve the marginalized zone with a high-resolution laser altimetry, like the ICESat-2. But both these panels all have high resolutions. About the radar altimeter, is pretty due to the relative cost resolution, it's pretty hard to retrieve marginalized zone with radar altimeters. So in this research, I hope to research the potential to retrieve marginalized zone with Cryosat-2, which the key panel is the Ku-band delayed Doppler radar altimeter. And actually, over the past 30 years, the radar altimeter has experienced a rapid development, and now radar altimeter has been widely used for the polar region. But for the research on marginalized zone, since the Professor Strapley's work in 1984, he tried to retrieve all the significant wave height in marginalized zone with CSAT, and then define the wave-affected marginalized zone in Antarctic. But however, after these works, there was no continuous works about this. So I hope to restart from Cryosat-2. And here shows some key knowledge about CrossSet2. Actually, CrossSet2 has been widely used for the asynchronous retrievals. They mainly based on the delay time between the transmit and receive the path, and then they can calculate the surface heat. Except for the delay time, we can also obtain the waveform, which describes how the waveform power changed with time. And for this spatial delay Doppler radar altimeter, like CrossSet2, it also provides the waveform stack parameters, which describes how the waveform power changed with different local angle. So we believe that based on the waveform and the waveform stack parameters, it's possible to identify different surface types. And here shows how CrossSet2 were observed over polar ocean. And we can see here when transferred from ocean through Magellan Zone and into ASPEC, the waves will attenuate in Magellan Zone, and it will also break up the flow in Magellan Zone. And for the lower shows the waveform and the waveform stack for different for typical surfaces, ocean, Magellan Zone, ASPEC, and LEAD. And we will mainly focus on these key waveform parameters. Firstly, we can find that over the waveform power in ocean are higher than that, are lower than that in ice-covered region. It's mainly due to the difference of the backscatter properties of the ocean and the flows. And I also hope to focus on the trailing edge of the waveform. And we defined the TS, the trailing edge shape with these functions, and we can find that the TS in Magellan Zone are higher than that in ASPEC. And I also hope to introduce the stack standard deviation SSD, which describes how waveform power changes with different log angle. And we can also see here the SSD in Magellan Zone are also very high than that in ASPEC and comparable to the oceans. Thus, we believe that based on the waveform and the waveform stack parameters, we can define where it's affected by waves. And here shows two cases of CrossSet2 tracks in Barents Sea. For that day, there was no storm, and 3 days later, there was a heavy storm. And for the lawyers, we can see here when 3 days after the day, and the first case, and we can see the significant wave height. It was very high, it's about 4 meters. And the lawyer shows the along-track CrossSet2 waveform parameters. And I hope to focus on the first 9. We can see when it's from open water to Magellan Zone, the signal will increase immediately. And when it's from Magellan Zone into ASPEC, the TS and SSD I introduced before also shows the gradual decrease. And in this case, we observed a very wide Magellan Zone, and the length was over 215 kilometers. And it's very longer than that retrieved by CS concentration. It's shown by the purple. And I also compared the end location of the Magellan Zone retrieved with star image. And we can find that the relative difference between these two panels are less than 5%. And based on this algorithm, I proposed the retrieval algorithm for wave-affected Magellan Zone, and I defined the start and end location based on the sigma naught and the SSD. And then we calculate a long-track Magellan Zone length, and then we need to project it to the normal direction of local sea ice edge and get the Magellan Zone width. And besides, I also compared the coincident tracks with ISAT2 and CrossSet2 and compared the retrieval results with these two different panels. And for this case, there was also a star image. And here shows the end location of the retrieval by these 3 different panels. And we also find that it also shows a good consistency with the 3 different panels. And we further connect 21 coincident tracks of CrossAir2 and SR2 based on CrossAir2 ICE program. And it also shows a good consistency between these two measurements. Thus, we believe that based on the retrieval algorithm with CrossAir2, it can provide the same precise measurements with the marginalized zone, same like the SR2. And based on the before mentioned retrieval algorithm, we generate a 12-year marginalized zone climate data record in Atlantic Arctic. And here shows some statistics parameters of retrieval by CrossAir2 and sea ice concentration. Considering the different ice conditions, we separate the whole research region into 3 different parts, and for each year we separate each winter into 2 parts. And we can find that in Barents Sea for the top, this top, and we can find very wide marginalized zone retrievaled by CrossAir2, and it's very longer than that retrievaled by CS concentration. And for different 3 regions, it all shows large interannual and intraseasonal change for both 3 regions. But we didn't detect any change trend of the marginalized zone width over the 12 years. And we also compared the retrieval results with the CrossAir2 and the CS concentration. We can find that the CS concentration-based marginalized zone was systematically lower than that CrossAir2 result. And there was only weak correlation between these 2 retrievals. That we believe that the CS concentration-based marginalized zone can't resolve the wave-affected part. Finally, I want to give a brief summary. We proposed a new retrieval algorithm, and then we generate a climate data record for the marginalized zone. And actually, we also established a new estimation of the swell decay in marginalized zones. But due to the time limited, I didn't have no more time to introduce this part. Yes. And that's all I want to share. Thank you for your listening.
Thank you very much. Thank you very much for this very interesting talk. Is there a short question? If that's not the case, we are a little bit over time, so please use the opportunity in the break for more discussions on the topic. We heard several talks now about altimetry with Cryosat and ISAT, so I'm sure there's a lot to discuss. I want to move over to the next speaker, that is Andreas Preußer from the Alfred Wegener Institute in Germany, and he will speak about interannual variability of snow and ice thickness across the transpolar drift as derived from drifting sea ice mass balance buoys. I guess you manage. The floor is yours.
Correct. I'm sorry. Okay. Cool. Yeah, good afternoon, everybody, and thanks for the committee for the opportunity to present at this nice occasion here in Tromsø. I'm Andreas Preußer from the Alfred Wegener Institute, the CS Physics section there, and yeah, I want to introduce you to the topic of CS mass balance buoys today. But first of all, I want to zoom out a little bit and show you an image of the coupled Arctic climate system, or coupled Arctic system. The sea ice right in the middle of the stage. And what you directly notice is that at the snow and sea ice interfaces, there are a lot of processes happening, interacting with or at the ice, ocean, and snow interfaces, and varying, of course, over the course of the year seasonally. But you notice that the thickness of the sea ice and the snow is quite central and crucial to a lot of these processes in various ways. We saw already that there's many different means of observing all these different properties, and also like the central parameters connected to thickness. But they all come with their certain scale challenges attached. So, of course,
it's always nice to have, the in situ measurements taking place on site, but you don't get the scale extent that you have by using satellite and airborne measurements. So to bridge this gap, there's a lot of autonomous systems deployed on the Arctic sea ice, measuring below and above the surface and also within the sea ice, that can bridge these on-site gaps, and that also provide data for regular data evaluation, exercises and process studies. And the instrument I'm working with mostly is a so-called thermistor buoy or SIMBA buoy. SIMBA buoy stands for Sea Ice Mass Balance Apparatus, and the name already implies it's meant to give insights about the mass balance of snow and sea ice. And it does it by utilizing normally 5-meter long chain with some 240 thermistors attached to it, and also heating elements that are able to give indications about where the interfaces are located due to their differing thermal properties. At AVI, there's a big archive now of over 100 thermistor buoys, also from partner institutions, not only from AVI. But they're centrally stored there, and you see in distribution maps in the northern hemisphere and the southern hemisphere where they are deployed and drifted. And you already noticed that there's a heavy focus on the Arctic, not only due to the, not least due to the MOSAIC campaign in 2019-20, where a lot of systems were deployed in a local array. But until recently, there was no consistent snow and ice thickness data set that was worked on or retrieved from these buoys. And that was the focus of Migrant project, which is situated in the Arctic Passion project, a huge EU-funded project consortium. And its work package 1 is dealing with enhancing instrumentation and data analysis in the Arctic. And there we come in with our SIMBA buoys, and our major goals there were to develop a uniform processing scheme to get a consistent data set of snow and ice thicknesses. That is, adds value in terms of characterizing the sea ice mass balance, and also is able to then assess more on the interannual variability of these measurements and interdecadal changes. I don't want to go into much detail about the processing itself, but you basically see that there's a processing chain. So starting with the raw SIMBA data, we then make use of the temperatures that are recorded, and the heating temperatures derive like attached properties, so gradients and thermal proxies. And then via manual classification approach, we can then derive the interfaces in a quite high accuracy. So at the moment, we have around plus minus 80 buoys processed via this chain, and there's more coming from the 2023 deployments. Which yields consistent time series of ice and snow thickness, interface positions, and temperatures. As not mentioned before, the interface detection is really the challenging, most crucial point to get that in a good error margin. So the submission to Pangaea is underway now, and for everyone's interested in using this data set is soon able to do so. This is what it looks like. I mean, the measurements from an exemplary SIMBA buoy. You see the temperature involvements, the thermal proxy over here, so the ratio of heating temperatures, gradients, and also the resulting snow and ice thickness with their error margins. And we can then add some additional properties by forward and backward tracking of these buoys, coming from atmospheric reanalysis data and also remote sensing products, which really tells you the story of each individual buoys, where they come from, and also what, for example, caused their breakdown at the end, usually in Farm Strait. Another thing you can do, and Yevgeny will likely talk a lot more on the MOSAIC case studies, but you can if you have like focused campaigns like the MOSAIC campaigns, you can really infer seasonal developments from these buoys. Here you see the, if it plays correctly, the seasonal evolution of vertical temperature profiles attached to the evolution of snow and ice thicknesses in this digital distributed network of Simba buoys, and this is a really neat data set to have now, and as I mentioned, the following talks by Yevgeny will show you more what's possible with those data sets if you have a lot of buoys in a single spot, so to say. I utilized now here a larger collection of Simba buoys, so the whole archive we have available in the Transpolar Drift from 2012 to 2023. That's, oh, sorry, the lower axis is the years, and then we have the monthly overview here. And on the top panels, you see the changes in eye thickness per month. So blue colors indicate growth, and the reddish colors indicate decay. For both eye thickness and snow thickness, and already put them in the individual interface changes. So the changes in the atmosphere-snow interface, the snow-ice interface, and the ice-ocean interface. And what you can see here in these plots is that also in this data set, why not, well, let's say it differently. It is visible that you also see the well-known effects of the earlier melt onset happening in the spring season, and also later freeze up in the autumn season. And this is likewise to see in the change of the ice-ocean interface. So a very nice observation there that we have this relation to the ocean. And the snow, on the other hand, is overall highly variable, and that is the same as a atmosphere-snow interface. And we do see, not surprisingly, but in several years, especially towards the last years, that we have really high surface melt rates of over 20 centimeters and more happening in Fram Strait, which is quite an interesting observation to see, and now interesting case to explain more. But yeah, in general, the bottom growth in mud is usually dominating the eye thickness evolution, as known. Scaling it up a little bit, because remember, these buoy measurements are point measurements, and of course, there's certain uncertainty related to that fact. But we do want to, or we did want to check how these buoy measurements are representative for the wider area surrounding them, and that's why we made a first attempt to compare them with the Cryosat-2 SMOS data set we have at AVI at hand. An example is on the lower upper left corner, and you saw from Robert's talk already details about that, or related data. And you see that the relation for single individuals can be quite good. And if you look at the distribution for all buoys, you notice there are certain buoys that are, of course, not as representative as others. There's also some artifacts still hidden there. But in general, we're quite confident that, we're quite comfortable that many of these buoys were deployed at quite representative deployment sites. Okay, I'll leave you quickly with the conclusions. So we have a new data set spanning 10 years of buoy data. We have now data that is able to get more details on the long-term analysis for local CS mass balance. The satellite comparisons were quite reasonable, and we also have this interface temperature now available for further validation exercises. A brief advertisement before ending. We have in February the upcoming third Mosaic Science Conference happening in Potsdam. So anyone who's interested in learning more and discussing more on CS mass balance buoy measurements is invited to join this event, and more details will follow quite soon on that. And with that, I'd like to thank you for listening.
Yeah, thank you very much, Andreas, for this very interesting presentation. Is there a short question? Yes, please.
How accurate are the measurements for snow thickness and ice thickness? Or like it's very, like I know nothing about in-situ measurement. So how hard it is to see the interface between the snow and the ice, for instance?
Well, in general, the accuracy is, of course, dependent a little bit on the sensor spacing, and usually those thermistors are 2 centimeters apart from each other. So in the best case, you have an accuracy of around 2 centimeters. But of course, you have often quite some ambiguities happening at the interfaces, which lead to an added error of 2 to 8 centimeters approximately. Yeah.
Thanks again, Andreas. And then we come to the next speaker, Lu Zhou. And she will speak about deciphering Arctic Atlantification, a detailed analysis of sea ice and snow mass balance over recent decades. Lu Zhou is also from Tsinghua University in Beijing, China. You're welcome, the floor is yours.
Yes. So, good afternoon, everyone. Yeah, okay, cool. My name is Lu Zhou, and I'm from the IMO in the Utrecht University in the Netherlands. And my today's topic is about the last decades of the ice mass balance coming out of all the export from the Frem Strait under the context of the Arctic Atlantification. And this work is also collaborated with my PhD supervisor, Shi Mingxu, from the Tsinghua University. And so what is the Arctic Atlantification? So this idea is first proposed by the professor Igor Polyakov. And this is basically talking about how the Atlantic water influence the Arctic climate change. So like the red arrow shows here. And also basically both the Frem Strait and the Barents Sea opening are the two main gates that the Arctic or the Atlantic water influence the Arctic climate change. And so some permanent or the related topic, including they were induced the atmosphere cooling, which were amplified this warming of the north of the Barents Sea, also the reduced freshwater inputs, and also a stronger influence in the sea ice import through the Barents Sea. And also, we've also witnessed the enhanced the upper ocean mixing and also the atmosphere ice ocean, the coupling within the Eurasian basins. So since the 21st century, the Polyakov also mentioned about when the mixture depth is getting warmer and the halocline is getting weakened, and also we've also witnessed vertical mixing layer, vertical ocean mixing processes is getting more easily and effectively. So this is how the Atlantic, the Arctic Atlantification works. And until recently, the Polyakov also mentioned about in the atmosphere when after the 2007, when the Arctic dipole, which is basically describe the two centuries of the sea level pressure anomaly located both in the western and eastern part of the Arctic, can change the wind pattern of the Arctic one, and then that would be inducedly affect the the surface ocean current both over the Frem Strait and the Barents Sea. And of course, from the sea ice itself, what we observed is after a long time, the ice thickness lost since the 1980s. What we saw is since after the 2007, the sea ice thickness loss within the whole basin, the basin scale seems to stopped. And we've also heard the slides from the Sumatra about their literally mooring observations and how the sea ice thickness regime changed after 2007. So as Robert and also Wei-Xin mentioned, we also monitor this ice thickness from the satellite. So that enabled us to calculate the winter accumulated the ice export from the Frem Strait one. So here, the purple lines are the kind of export, wintertime accumulated ice export from the mooring observations, and the red lines are from the simultaneous retrieval method from the CrossAir2 and the SMOS one, and the green lines are from the ICER2 and SMOS one. So although we witness there was a large inter-variability within the CrossAir2 retrievals, but we did have some confidence in this ice export from the different resources, including the observations and from the satellite remote sensings. And we did find there was some congruent or consistent study within this, the ice export, and without no significant trend since the past 15 years, starting from 2010 until the 2023. And also, over the last decades, the lower the Ter also find over the Arctic outflow which is southward, is going to like a significant increasing. And also, what we observed from the, what we observed from the ocean, the reanalysis glory data is what we find a significant positively trend within the Frem Strait that indicate us that the Atlantic water is going to intrude this or pass through this Frem Strait increasingly and produce more heat or more temperature anomaly. So we take into account to calculate this southward freshwater flux and northward, like Atlantic water, the transportation. And we find that since 2007, they all in the stable in a quite new but higher stable state line. And when we further take these observations into account, we take a close look at the mean temperature and the salinity vertical profile, like after the 2007 and during the 1990s. What we find is during the eastern part of the Frem Strait, which is understandable because of the Atlantic water intrusion, the temperature and the salinity is getting higher and getting saltier than before. But the western part of the Frem Strait, which is quite tricky because on one time, there's the southward freshwater flux effects. We witness the salinity profile on the bottom right is getting fresher than before, but the temperature is only getting cooler during the later winter and only within the depths of about 100 meters. And above this 100 meter, we still saw the temperature within the ocean is warmer than before. And if we take a close look at, or to calculate the ocean heat content within the Mixler depths, both over the Frem Strait and over the Barents Sea, what we saw is this winter accumulated, the ocean heat content is increasing as expectedly. And further, if we correlate with the ice export from the Frem Strait, we found that the Barents Sea, the polar world, the ocean heat content can explain at least 30 to 40% of the interannual variability of the ice export from the Frem Strait in ahead of a 2 years time. And this 2 years leading time is exactly corresponding to the satellites observed the atmosphere surface, the net downward flux over the Atlantic region. So talking about atmosphere components, so as we saw, the Polyakov already mentioned how the large scale, like atmosphere, can affect the ocean current. So here we also bring about the two terms. The one is jet stream, which is consider about the jet stream is talking about the narrow band with a strong wind on the upper level of the ice of the atmosphere, and we literally saw after 2017 And I need to mention that the location and the strength of the jet stream is highly correlated with the ice export, either impede or to promote the ice export. And we literally saw after 2007, both, no matter the jet stream, the jet stream itself changes into the lower speed, like the speed value, which also bring about the another transition, because the indication from the ice export from the jet stream is transfer from the later autumn to the later summer to the earlier summertime. Another phenomenon I want to bring about is the atmosphere river. So the atmosphere river is more about the strong and long, the flowing concentrated, the belt that contains water vapor in the atmosphere. So what we also saw in the upstream, this is north of the American region, what we also saw, this atmosphere river activity is going to increasing in the north of the American regions in July, and also in this north of the Atlantic regions in the September region. But this is like ongoing study, which we need to explore more about how atmosphere river or atmosphere affect the ice export through the Fram Strait dynamically and thermodynamically. I'm not going to give you like final conclusion, but the more questioning about how we are resolve this kind of a complicated atmosphere ice ocean interaction, including how to attribute the atmosphere and Atlantic water in contribution the ice mass balance coming out of the Fram Strait one. And the other like missing gap will be including how the ice and snow albedo feedback changes under the context of this the current Atlantification period. So I will thank you for your listening.
Thank you very much for this very interesting talk, and apologies that I missed your Netherlands affiliation there. Is there a very short question? One thing I wondered is the role of snow, changes in the snow. Is that also one of the question marks in the next steps you are looking at?
We literally have the snow like volume output, but the snow, the output, we do not have a long time. The observation only from the 10 years from the satellite one. So we were looking forward to more possible like investigation and analysis one, and including from the model and from the remote sensing.
Yeah, cool. Thank you. Okay, thanks again. And then I'd like to move over to our last speaker of the session. That is Evgeny Salganik from Norwegian Polar Institute here in Tromsø, and he will speak about representativeness of ice mass balance buoy measurements during the Mosaic expedition. Evgeny, the floor is yours.
Thanks a lot, Sebastian, for the introduction, and of course I'm very grateful to all my colleagues and collaborators from various institutions from Mosaic. So let's start. So the questions I tried to answer in this small study, it was how representative these ice mass balance buoys introduced by Andreas 2 talks before are for Mosaic observations, and can generally they improve the large-scale observations of ice mass balance in the Arctic region. So then, of course, the first question is, so the aim, and here's a link to one of my favorite studies by Jack Landy, the leader of our project, is, so this is the ice thicknesses in various seasons in the Arctic from Cryosat 2, and while this looks really impressive and it would be great that it would be absolutely 100% accurate, but there are some of course issues here. For example, if you take May and July, you see there's a huge difference in thicknesses, but if you see the typical ice thickness evolution over from the forward-looking sonar, for example, in this case, you see that actually early May and early July usually have very, very comparable ice thicknesses. So it's ice is not growing and not melting that much in this time. So, yeah. Thank you. So why Mosaic? This is a Mosaic ice drift, and its answer is very simple. It allows to compare altimetry and buoys estimates and many other additional measurements on completely uncomparable scales. So let's start. This is the ice thickness evolution from the product from Landy and EM estimates over flights of Mosaic ice flow over the season of Mosaic. And you can see, of course, pretty clearly that while in the beginning and until February, the thermodynamic ice growth is captured pretty well. Then, of course, during these ice warming events, we all know that a lot of snow is treated as ice, and we have this artificial huge increase in ice thickness, which is later on during snow melt. Of course, returns back and decrease our estimates of accuracy estimates of melt rates, while late melt estimates after most of the snow above level ice is melted is actually pretty good. If we compare with a little more local transect from EM, Grand EM, it's a transect of several kilometers long, you see that most of the things are captured. And if we take the buoy observations Andreas introduced, you see that buoys, again, capturing the whole processes pretty well, but if in terms of ice growth, this 3 kilometer long whole transect can be described by only buoys, which had a similar initial eye thickness, so the upper ones. Okay, so this is of course the important takeaway that IMBs can be used and should be used, but of course you need to know that which ice types are represented, and then for that there is a great study from Venkagor about the fractions of different ice types for the mosaic ice floor. And luckily, since there were a lot of ice mass buoys, the fraction of this deformed and deformed ice was pretty similar. But when it comes to ridges, so very big ice, very deep ice, it's trickier because there is a very large scale estimate from Robert Ricker from his mosaic paper, which I multiplied by 3 because of the rich statistics, which is completely uncomparable for this transect I mentioned with much heavier ridging. So why ridges are important? So yeah, the ridges, their lifetime looks like this, which is pretty simple. And the thing is that they cannot be described properly by ice mass buoys because of obvious reasons. They're constantly formed, and you cannot add every month several buoys in ridges. So in addition, what is important is that they have really much more complex hydrostatic balance. So they generally kind of stay in the same level in the cold season. Then when snow, and they have a lot of snow, 3 times more snow than any other types, they go up, and they start to melt, and they go down, which is of course very important message for how they are treated by altimetry. All right, so for representativity, I guess it's pretty logical to divide things in 2 seasons, cold season and warm season, and the key parameters to understand how representative ice growth and ice melt are as following: the snow depths and initial ice thickness for the winter season and for the buoy interpretation. And for the melt season, it's a bit more. It's about ridges, because ridges we showed are melting much faster than level ice. A melt pond fraction, because ice mass balance buoys unfortunately disturb the radiation surface balance, so they tend to be ponded more heavily than on average. And ice thickness distribution, right? Because some ice types are melting slower. So for winter season, everything is pretty good with buoys. So even with a limited amount of buoys, I worked with Mosaic. You see the main things which are observed with much larger these transect observations of several kilometers. You see that generally the thicker ice, the red one, has more snow when it's getting thicker. Well, if it is thicker, and you see that deformed ice has approximately 3 times deeper snow. So even a limited amount of buoys is pretty good in describing that, both in values and the trends, and similar with eye thickness. And this comparison with great, can I go back? Yeah, with this great a study from Luisa von Albedil about EM measurements during Mosaic. For the melt season, it's a bit trickier, right? This is a study based on underwater sonar during Mosaic, and we tried to estimate which level ice is melting faster. Pretty obviously, on these small scales, like 100-meter scales, thick ice is melting faster because of the turbulence and the meltwater certification. But for the buoys, I mean, of course, there are different scales, right? They're much more further away from each other, and you don't see that trend. And there are two potential explanations for that. So you don't see the trend that thicker ice is melting faster for undeformed ice from the buoys. And there are two potential explanations. First of all, you see huge variability, and in addition, we're talking not about, I mean, it's not the thickness is controlling the melt and enhancing the melt. It's the relative thickness to the mean thickness in the area. And the final thing is, I guess it's very important, what actually we are measuring during the melt season, and can we measure the ice melt only from the freeboard? Because what we saw during Mosaic, that during the relatively, like half of the melt season, is that despite level ice was melting, it was going up, which is pretty sad for any altimetry, satellite altimetry, and helicopter altimetry. So despite 50 centimeter of melt, actually the ice went up. And this is because the gas bubbles are, only for first year ice, are increasing in volume dramatically during the warming. Then there are great theoretical studies explaining that. And despite that during this July-August thing, the product from Jack Landy actually explained almost perfectly the melt, the melt rate, unlike before during the snow melt. We actually have to answer ourselves, like, what actually are we measuring? Is it only a melt on the freeboard decrease of thicker ice, second year ice without bubbles and ridges, or is it actually something average? So they take home messages. So they generally, as mass balance buoys, give very representative values of snow depths and melt rates in comparison to the other larger scale observations during Mosaic. The ridge contribution should be included additionally as a ridge fraction and thickness, which can be done from upward-looking sonars or from altimetry. And early level ice melt cannot be captured due to density decrease for first year ice, not for other ice types. And I think that's it. Thank you for listening.
Yeah, thank you very much, Evgeny, for this very interesting talk, and I open for questions. Yeah, I wanted to ask, what do you think are the biggest challenges when using ice mass balance buoys for understanding the changes you talked about?
I think the biggest problem with ice mass buoys is they don't measure freeboard. I mean, it would be great to have a very accurate pressure sensors on all of them to know what's happening with the freeboard. I mean, otherwise, I think there's in its scale so much more precise than any other measurements, and they are not affected by many other artifacts from meltwater and so on. So generally, the buoys are not an issue. It's like our understanding of hydrostatic balance of different ice types is an issue. That's my understanding of the problem.
Yeah. Oh. Great. Then I want to close this part of the session, but remind you that there is a poster session this evening in Fram Center where their posters connected to the session are shown, and there are 2 more parts of the session tomorrow morning before lunch tomorrow. So please check in then again, and thanks very much to all speakers and to all who contributed to the discussions, and have a nice break now.